Вот, по-моему, Саша, по-моему, к Xiaomi.
Ничего. А,
Я думаю, это
а,
на нет.
да, мы начинаем наш очередной семинар, но прежде чем начать, значит, я думаю, что многие уже знают, что э, в субботу скончался Василий
Ага.
Михайлович Бабич. Вот. И э, я прошу м, почтить его память.
Мгм. Да.
Спасибо. Uh, Now we can start our seminar. And today our speaker is Professor Luang Hoang from Texas Tech University. Please, Luan, you can share your screen.
Okay, thank you. Good. You can see my screen now.
Yes, yes, okay.
Okay, should I start?
Yes.
Okay, thank you very much, everybody. Thank you for the invitation and thank you for coming. I know that it's kind of late afternoon in St. Petersburg or Moscow or somewhere else. So thanks for coming. Today, I will present a recent research of mine, at least, a class of anisotropic diffusion-transport equations in non-divergence form. This is a joint work with Akif Ibragimov, and it's based on our recently accepted paper. So this is the outline of the talk. First, I will have a very short introduction about the method based on Einstein's probability approach to the Brownian motion. Second, I will derive the models using the first the general equation about the movement of particles, and then we make the main assumption relating the probability quantity with the velocity, and then we apply it to the fluid motions in porous media. After that, we will do pure mathematics by analyzing the resulting PDE. We will use the Bernstein, a Cohnhoff timed transformation, and then prove the strong maximum principle. Then we study the initial value problem and derive maximum estimates for both linear and nonlinear problems. Okay, please, if you have questions, just interrupt and ask me anytime. And if we have problems with the transmission of the signals, and then tell me so that I can turn off my video if needed. So this is the introduction. So we want to study the general particle movement. So because I and Akif did research in porous medium equations, so we start with an example on the movement of fluid in porous media. So traditionally, it is based on the three components. First is that the conservation of mass. The second is that the equation of motion, either Darcy law or its generalizations. And the third one, at least for is the equation of state, which is important when we deal with compressible fluids. So usually these three components lead to partial differential equations of parabolic type, usually nonlinear, and degenerate equations. Thanks to the equation of mass, the mass conservation, which is in the form of equation of continuity, they usually appear in the divergent form. So our approach is to replace this equation of continuity by using Einstein probability material balance to derive a partial differential equation for the density of this form. So we have the second order is in non-divergent form, but then we also have the first order, which is the transport term. So in Einstein's approach, this transport term is zero. So now we do it in multi-dimensional and assume that it's not zero. Now this is the probability level. But then we connect this e to the tau to the macroscopic quantity velocity, and combine that with the Darcy law and the equation of state, and we will derive a nonlinear PDE for rho. Okay, so that's the sketch, the outline of our program. So we hopefully that with this naturally obtained parabolic equation of the non-divergence form, now people can study more about the dynamics of the non-divergence parabolic equations. So next, this is the derivation of the models. So as I said before, first we will use the Einstein approach and then make an assumption relating the microscopic to the macroscopic quantities, and then apply to the movement of fluids in porous media. The first one is that we consider rho as a density, tau positive is a small time interval of observation. Now, zeta is a random distribution, random displacement of the fluid particles. Then assume that we have this probability distribution function for this probability. So it is from location x at time t to location x plus zeta at time t plus tau. So this is the probability distribution function. So we have the integral is 1. Now the Einstein's conservation of mass in this case is written of the form that we have the density at x at time t plus tau equals the integral of the density with the probability, okay, rho, phi, with any random displacement zeta. So this will be our starting point using this conservation of mass. So for tau small, we will do the normal approximation by the quotient in t. Now with the first density rho of at t plus, okay, wait. Now, the first one, we will use the probability representation of the density, like this. Then we do the Taylor expansion in the spatial variable with respect to the random displacement zeta. So we will have that rho plus zeta dot grad and plus the second order derivatives of rho. So we rewrite, of course, the first one here will be the density itself. The second one, we will pull out the grad rho and then denote the rest by the vector E. And similarly, we will do the same for the second order. So if we redenote, we will have that E is this probability quantity, and Aij are usually defined by like this. Okay, so then we subtract rho from both sides and divide it by tau, and then the left-hand side we consider it as the time derivative of rho, and then we have the second order plus the first order. Okay, so we write in the form of the product of two matrices. So this is the general equation of movement of particles. But now the quantity E, the vector E here, so we do one more step to relate this one to some macroscopic quantity that we know.
Excuse me, Luan,
Yes.
a question. The matrix A is matrix A, no, the resulting matrix A, no, it should be something like A bar divided by 2 tau.
Yes. That's what
Yes.
I did not write out the definition, but you yes.
Okay. Yeah.
Yes,
okay.
you are quite correct, but I saved space, so I did not write down the definition of A.
Okay, thank you.
Yes, you are quite right. Aij bar over 2 tau. That's matrix A. Yes, thank you. Now this is the main assumption. we jump. Okay, so E. If you look at the definition of the vector E, so you have probability times the displacement. So it can be seen as the expected displacement from location X, from time t to time t plus tau. So with this equation, so it's divided by the time of travel tau. So it's like the average displacement divided by the time of travel. So it's just the average velocity. And also, if you check the dimension, they match. The E over tau and the velocity, they match the dimension. So we assume that, in fact, that this kind of approximation of the average velocity is proportional to V. But everything is approximation. Even tau is not there, is not zero yet, doesn't go to zero yet. It's finite and positive. So we assume, okay, this is our main hypothesis. We assume that the vector E over tau and vector V can be related by a matrix M0. And M0 is like positive or non-negative like this. Okay, so why we put this condition, even though mathematically later on we don't use this much, but to make sure that E and V are kind of aligned, not exactly parallel, but they are of the same direction. Okay. So with that one, so here, what I said, so V and E over tau with the last condition is kind of same direction, but not exactly parallel. So we obtain the very general equation for the density. After that, now we use the standard law in the fluid motion in porous meter to connect that to the pressure P. Okay, so with that one, we have equation for the rho with the pressure. Remember that here we use the form with the rho, so that's why rho also appears. So already we see that this is a nonlinear equation for rho. Okay. Now we do one more. So we use equation of state to relate rho and P. So with that one, for example, for isentropic gas flows, we have a nonlinear PDE for rho with the quadratic gradient terms with and the nonlinear term of rho. So we have nonlinearity in the quadratic gradient or the gradient and the rho itself. In particular, for ideal gas, so we have purely quadratic without the power of rho, and the second one. So each of them is just a bilinear term. One in grad rho and one in grad rho and rho. For petroleum engineering, we usually deal with the slightly compressible fluids. So with this one, we will have another equation for rho with the potential singularity for the quadratic terms grad rho squared. So these, okay, so now in general, we can have the general equation of state P equal P0 in an interval J, okay, and derive the general PDE for the density with the nonlinearity quadratic term for grad rho potential inclusion of the mode nonlinearity for P0 prime, and also the nonlinearity in the form of the bilinear form of rho and grad rho. For example, for non-ideal gas flows, and we have J is 0 infinity and P is h to the gamma. For the ideal gas, we can either consider the physical U as a density, or we can write equation for U, just a mathematical quantity. So we can have either J is positive, is from 0 to infinity, or J is the whole R. Because in this case, PS is easy, PS is S. Now for slightly compressible fluid, we have to restrict to positive numbers only and have PS is log of S. So we do it very carefully here because then we don't really know what is the general equation of state. So we want to put as general as possible. So the interval J here, of course, if it's bounded, and then there is no point to do the maximum estimate. But most of the cases, as you will see here, the J is unbounded, at least one-sided. Okay. So next is we study the equation mathematically. So we start, our main method will be the maximum principle. So first we try to, even for nonlinear problem, we try to get the nonlinear strong maximum principle. So we consider the fluid is in the bounded domain, bounded set, and A is uniform elliptic, and B is a given function, a vector valued function. Now J, we assume that is an interval, of course not a one point, just an interval. It can be open or closed or half open, half closed. And P is C2 function, which is increasing, So our equation, okay, the nonlinear operator will be this one. So you have the linear part plus the nonlinear part. So the nonlinear part, we have the part with the u and grad u, and then particularly you will have the part with the quadratic term of the gradient with the possible nonlinearity attached. So with this one, because then all of these things, we don't have the free term. We don't have the free term Cu. Okay, so that's why that if you start with the classical solution, the nonlinearity with the gradient of u doesn't hinder the maximum principle. So even for this nonlinear operator, we still have the maximum principle for any subsolution of L. It means the LU less than or equal to 0. So we will have the maximum principle. Okay, so now that's when you do consider the nonlinear problem, while you fix all these things, and then we can easily have the maximum principle. But to do the strong maximum principle, these now play the role. Okay, then you have to do some transformation, and the transformation, amazingly, is of the Bernstein-Kornhoff type. Even with now in the literature, they usually say Kornhoff, but in fact, that Akif and I checked old papers by Bernstein. It seems that he had everything we need. So it's back in the 1905 or 1912, in fact. So we will rewrite the nonlinear operator in the form of linear one with, okay, we combine the last two. Whoops, sorry, why? You combine the last two terms, okay, into one term like this. Good. So what is the transformation? The transformation, okay, sorry, wait. The transformation, okay, so we take into account the P prime of U, the nonlinearity of P prime, and the matrix K. So we have the transformation of the form, the integral of e to the lambda, when lambda is a parameter, okay, together with a positive constant c and some number c prime. So this is our f. So then we will have f prime positive and lambda double prime is greater or equal to 0. So this is easy calculation. Now, if you have, this is not the positivity. So it means that if you only need the lower bound, even the negative lower bound here, okay, of the matrix K, then if you have a subsolution of the nonlinear operator L, the transformation with the lambda positive will give you a subsolution of the linear operator script L. So that's why you can transform a subsolution of the nonlinear problem to a subsolution of the linear problem. Of course, in this case, the linear problem have u as considered as a known function. Okay. So the proof is that so the wait before the proof. So that's when we have the sub solution. So you can do the similarly if you have the upper bound, and then you have the super solution of the nonlinear problem, and with lambda now negative, then the Bernstein's Kornhoff transformation will give you a super solution of the linear problem. So the proof is just do calculations. So you relate LW with LU. So F prime here is positive. Now, if you have a sub-solution, and then you remove the LU here, so you have less than equal. Then you have the conditions on the K. Okay. So with that condition on the K, and the ellipticity with F double prime is positive and lambda positive, then the suffocation condition is reduced to this when you have the upper bound, lower bound this, and upper bound this, and then you relate. And then instead of solving just the inequality, we just solve the equation. And then that's what we have with the function f here. So in the case for the super solution, it's just similar. But in this case, we consider lambda negative and f double prime negative. And then the same with the ellipticity and the condition, in this case, upper bound of k. And then we have these estimate. And then we do the sufficient condition, and with lambda less than or equal to negative C2 over C0, then we solve for equation instead. So in this case, then by using the Bernstein's transformation, we can have separate transformation. One transforms the sub-solution of nonlinear problem to sub-solution of linear problem, and another, not the same transformation, that transforms the super solution of the nonlinear problem to the super solution of the linear problem. So these are examples. If you have anisotropic gas flows, and then in general, gamma is greater than 1. So you have f lambda is like this. So you can see that the growth later on, if you want to study the maximum estimate, and the growth here is very, very large, very large. Okay. So for ideal gas, it's much simpler. So you have f lambda is s, or lambda equals 0, or exponential, or lambda is not 0. Now for slightly compressible fluids, we only have the power. For lambda not negative 1, and while lambda is negative 1, we have the logarithmic function. So these explicit one will help us to apply our general or abstract result to the specific fluids types in porous media. And of course, it also gives us more information and improve our estimates if we need. So strong maximum principle, more or less everybody knows that if you have the sub-solution or super solution, and if you attain the maximum in one interior point, then it is a constant, okay, before that time. Okay. So I will not give a proof to this one, because so the main idea is that you do the Bernstein transformation with positive lambda or negative lambda depending on sub or super solution. And with this one, you have the the sub-solution for the linear one, or super solution. And with this one, you have the strong maximum principle, and the f function here is kind of good. So then we can do the inverse and then have the strong maximum principle for U. Okay, so the main thing is just the Bernstein-Cohenhoff transformation. Okay, any questions? Now we move on to the initial boundary value problem. Our approach is to have the estimate for the linear operator first, and then for the nonlinear, we consider the using maximum principle for the very rough estimates, and then consider the nonlinear one as a linear one. So we introduce. So our approach is to use the growth lemma of Landis type. In fact, it's just the Landis growth lemma, but Landis has a couple of types of growth lemma. So this is one of them. So we take R0 is the minimum kind of distance from X0 outside of the domain, okay, to the domain. Okay. So then you have, we assume that ellipticity for A and boundedness for B and trace of A. In fact, you can assume A is bounded. Then you consider the linear operator L tilde. So here we study the linear one with the general B, vector B. Then the growth lemma of Landis type is that the maximum of, okay, for a classical solution and the sub-solution, and if on the boundary W is less than or equal 0, then there exists a number strictly less than 1, so that you have the maximum of the later time, but you have to wait a little bit for later time T star, so that the maximum of the time T star is strictly less than maximum of the initial time 0. Okay, so that's a Landis type, and everybody knows that later on this kind of growth lemma helps Safonov and Krylov and Safonov prove the Harnack inequality and C alpha results for non-divergent form. So the proof, let me see if we have time. The proof is that we construct the barrier function. So everything follows Landis. And with this one, we have a sub-solution, but our real barrier function is this one. So we have a super solution. So when you compare the sub-solution W and super solution W tilde, so we can check the boundary value as well. So then at the time T star, you will have the estimate, and then with the particular specific calculation, you have this is the eta star times the maximum. So M here is the maximum. Okay, and eta star is written explicitly for some number D0 and D1. D0, D1, we can easily calculate. Okay, here I did not write explicitly, but you can easily calculate using this specific function phi. So that's that's the growth lemma. Now, if you apply the growth lemma on consecutive time interval, of course, then you will have the estimate for all time. So estimate for all time, we assume A and B are defined for all time, positive, and we have the standard ellipticity and boundedness of A and B. Now, with the particular specific definition of the parameters here, so after you weight T star, we know that the solution has to decrease strictly, right? So now we have a proposition is that if you have the classical solution, so if it's a sub-solution, and then you have it decreases, at least for small time, it strictly decreases for small time. For all time, okay, so when I say strictly decreasing, that the constant here is less than 1 for T positive. Now, for all time, we have to sacrifice a little bit. So we have the exponential decay, but with the constant maybe greater than 1, with the greater than 1 constant here. Okay, it's a little bit trade-off, but we have both the estimate for small time and large time. So this is for sub-solution. Then you do the same for super solution. And after that, you combine to have the estimate for the solution, which is strictly decreasing for small time and exponential decaying for large time. Of course, then as a consequence of you have the limit of the maximum is 0 when t goes to infinity. So remember that all of these things that we have, that the boundary condition for subsolution is less than or equal to 0, and for the solution itself, it must be 0 on the boundary. So we call this like a homogeneous problem. Now the proof is that for small t, we will define all the parameter explicitly using the small t. And if you do this one, when you calculate, of course, everything still depends on t, and eta star now depends on t and have this form. So that's why we had the estimate for small time. Now for large time, we can apply the growth lemma for each interval. So for each interval, we have estimate. So it's decreasing strictly, Okay, so for each interval, and then you put them together. So in this case, you take the evenly paced in sub-intervals tk equal k t star. Then you have so you apply the growth lemma on each interval successively, then you will have the power decaying. So of course, and you rewrite this as the exponential decaying in eta in k. Okay, let me write down. And after that, if you compare the general continuum time t, and then we consider it belongs to this one interval, then we can connect and have the exponential decay. So that's the decay of the solution when t go to infinity for the linear problem. Now, for the nonlinear problem, again, we consider the matrix A and vector value B for all time. Okay, for all time, then we have we assume the ellipticity and the boundedness. And in this case, we assume more or less that K is bounded. Yeah. So K is bounded. Yes. Then you have more specifically, we have the explicit number M0 and M1. So with that one, we study the initial IBVP initial boundary value problem, but still, so this is the nonlinear problem. And then on the boundary, in this first step, we study, because here the equation, you can only have the grad u here. The main part is the grad u. So if you shift by a constant, it doesn't change much. So in fact, that here we assume that on the boundary, it is a constant. Okay, so this is some restriction, but later on we can do more, okay, and study the more general boundary conditions, even depending on time. But this is the first step. We consider the constant boundary condition. And we study the classical solution. Of course, then remember that here, P is a function. So that's the definition of P. So P is in the equation. So we have no choice to have to impose that if we study classical solution, U must belong to J for all J. Of course, our J will not be bounded in application. Now, by the assumption of the continuity up to the up to the first initial condition here. So we have, if we assume that M, small m star and big M star are minimum and maximum. So by of the initial data and by the maximum principle, okay, so you will have that, because then U0 have to be on the boundary at the bottom as well. U star, because U star is here. And then we assume everything is classical up to the corner here. So we must have U star between small m and large m star. Okay, so by maximum principle, we already have the estimate of U in terms of small m star and large m star. But we want the stability when t go to infinity. So this is the rough estimate. But we need that when t go to infinity, it should go to U star or not. This is our aim. So we study the stability when t go to infinity. And then this is the very picky consideration when you have to consider that whether that both m big large m star and small m star belong to the interval of definition of the P or not. So we consider some very particular case when even when you don't have it belongs to J, but you have the right-handed limit. Now the other situation is that the lower m star, the small m star is in J, but the large m star is not in J, and then we have another limit from the left. Okay, so you can see it here. So we don't know if M star and big M star, okay, belong to J or not. But you assume that you have the limit if they don't belong.
Excuse me,
Yes.
are you assuming some monotonicity of P or something like this?
Yes, yes. P prime is positive. Also.
Okay.
Yeah, we assume that, yes. We assume that from beginning. Yes, you're right. Yes. In fact, we need that because then even when you do the strong maximum principle, when you go from U to, well, okay, when you extend the equation up to the boundary, so we have to need a little bit. Anyway, so with this one, you can extend the exponential to a e lambda equation, including, let's say, the boundary, the possible borderline value. Okay, here, and then we do the same. We do the same Bernstein-Kronhoff transformation. So with that one, we have the theorem that, of course, the case, sorry, M star equal la M star is trivial. So we only consider the case when they are different, M, small m and large M star. So with that one, so the first easy case that everything is inside the interval J, then we have very nice exponential estimates, exponential decay estimates. Now the other cases are very picky, peculiar, when we don't have this, and then again, you have that one of them may belong to, we cannot deal with all cases, unfortunately. We only deal with either one of them belong to J and the other one doesn't belong to J. And in that case, we are able to have the partial estimate, only one-sided estimate. But in the case, particularly if in addition, remember U star is between M star and large M star. If you have more information on this relation after you have upper bound, then because of this one, you have the lower bound, and then you can conclude that the limit, you have the stability when t goes to infinity. But here, we don't know exponential decay or not. Okay. So in this case, we have the stability, but we don't know if it's exponential decay. So it's not as strong as a 4.1 here when you have exponential decay. Now the other cases are similar. So if you have something partial information, and then you have on lower bound, if from lower bound, if you have some kind of special relation for the upper bound, and then you will have it decays, but not necessarily exponential. And then you have other kind of cases as well. Okay, so the proof is that, so the idea is that use Bernstein-Kronhoff transformation, but we need to take care of a lot of details, especially the borderline cases when M star and small M star and big M star belong to the J or not. But okay, I give just the easy case when, okay, both belong to J. Okay, so the only thing is that we have to be careful because when you do Bernstein transformation, we don't have the same transformation to convert the solution to solution. You have to have different transformation to convert different types of solution to different types of sub or super solution, then you have to make sure that the partial information for each, when you put together, will give you the whole absolute estimate of the absolute value. So we just need to take care of that. Okay, so first we do the two transformation to convert to sub-solution and super solutions. And on each of them, we carefully using maximum principle mean value theorem, but only for, okay, so first we do the linear growth lemma to have decaying estimate. Okay, but remember that here we only have one-sided for each sub or super solution. Then for each of them, we carefully use the mean value theorem to have one-sided estimates. Now we put together growth lemma and one-sided estimates. It turns out that we have two estimates, okay, sided estimate, okay, upper estimate, in terms of the absolute value of W minus W star. W star is the F of U star, absolute value here. And then you have lower estimate. But now everything now depends on initial condition. So, but the initial condition is the forward transformation. So it's easy to relate this one to U. So with that one, okay, so you put together upper and lower estimates, and then you have the estimate for absolute value. So that's when we have the exponential decay. The other cases are similar, but we have to do it very carefully, considering some borderline cases. Corollary is that then when we move the initial time, when you move the initial time, everything now depends on the asymptotic behavior of the matrix A and the vector function B. That's all. When you move the initial time, so everything depends on the asymptotic behavior of B and A. That's all. Now we have example is that if you have the isentropic gas flows and everything now is good and you have exponential decay. Right? Now if you have slightly compressible fluid, and J is here, so the case M star equals 0 will be a borderline case. So in that case, we have a few scenarios. So in case of M star positive, then everything is good. So you have exponential decay. Now otherwise, okay, so it depends on cases. For example, I do it here. So if you have this borderline case, then you only, by our general theory, we only have the maximum go to 0, but not exponentially. But in this case, you have F is a particular form. So with this one, you can have more information. And then in this case, you have more information. And then you can go back easily from W1, which is the power of U, to U itself. So in this case, you actually have exponential decay again. Okay, so I think my time is up exactly. Thank you very much for your attention.
Okay, let's thank our speaker. Well,
Hoang, but you did not talk anything about drift problem.
Okay.
What do you mean drift problem? Everything with drift here.
But drift, you don't have a unbounded drift.
No, no,
You did not say anything about it. I'm sorry. But okay, it's okay. You just
No. You're quite right. Remember, this one, we do particular nonlinear problem, right?
Yeah, so with
Nonlinear problem, of course, you have drift. But drift here,
is bounded.
no, wait. This is a drift, right?
Yeah.
So not linear problem, of course, our drift is bounded. But for nonlinear problem, we assume u equal u star on the boundary, and u0x is here and here. So when you apply this one as a bxt dot grad u, so with this one, you have b here is bounded. That's why you apply the growth lemma uniformly when we go from tk minus 1 to tk. So this one growth lemma is designed to apply to the nonlinear problem, and then this nonlinear problem with kind of simple values, and then we have everything.
I just want to point out that you have
bounded.
Results for unbounded drift as well. This I just
okay, that for people to ask before we advertise. Okay, if Akib already said it, so we have a follow-up of this paper when we deal with time-dependent boundary data and then the bounded drift, unbounded drift. But that's the next project.
Okay, I have a question. Do you have some concrete situations that where you have indeed a non-exponential decay, or you simply don't know whether it is exponential?
Ooh, wow. Up to now, because we aim at bounded drift, and then our okay, just the easy example is that everything is bounded, so we have exponential decay for sure. Mm-hmm. But you touch is something very sensitive for me, and I keep looking into the problem. So there are two directions. One is that our next paper, okay, because I keep already forced me to advertise. Next paper, okay, unbounded drift. Mm-hmm. And then for unbounded drift, and then of course unbounded it can grow, and then if the unbounded drift grow, and then we don't expect exponential decay.
Okay.
The decay can be depending on the how the drift term grows.
Okay. Yeah.
So that's one direction. Another direction is that here you have the cylindrical domain in space and time. If you do non-cylindrical domain in space and time, even bounded drift, you don't expect.
You mean that the domain enlarges with time, yeah?
Yes.
Mm-hmm. Yeah.
Oh my gosh. Your question is so natural, and then we are writing a paper on this case.
Great.
And then even with bounded drift, we don't expect the the exponential decay. Yes, well, thank you.
Please, more questions or comments?
Can I ask the question?
Mm-hmm.
And my question is, what about the existence of solution to the nonlinear problem? Prove it in general situation.
You're quite right. Our result is more qualitative study. Now you know that
your result a priori result.
Yes. A priori estimates. Now, for the existence of nonlinear, of course, even the linear, only recently, because remember, this is a non-divergence.
Mm-hmm.
Okay, let's say non-divergence. So the non-divergent, it seems that it escaped many people attention. So then only recently I see that of course, not for classical solution, but for solutions of weak solution, but with many BMO, VMO, okay, or BMO, VMO, I don't know, remember, or LN drift. And the existence only recently by, I think, either by Krylov or his student.
Мгм.
Мгм.
Luan, we don't see anything. I'm sorry, you are writing, Luan.
What?
We
No.
don't see anything.
Не, no, we see, вот.
I don't see it. Maybe I'm wrong.
Ну, я не знаю, нет, я все вижу.
Okay, then it's good. Sorry.
Okay, so only recently, okay, especially for unbounded drift, but for integrable drift, not integrable, Ln drift or LQ for Q greater than N. So only recently that I saw some papers by, let's say, Krylov students, a group.
Мгм.
But
Thank you.
again, so I think that our derivation or equation will have to encourage people to look more into the non-divergence equations, especially for me, last time estimates, last time dynamics. Yes, that's all I know. And then Akib said that back in the 1980s, so some special cases. Oh, yeah. So Landis himself have some papers, but for linear problems. Existence of
Mhm.
some particular very specific examples. Yeah,
Мгм.
yeah, that's
you.
I can say. But we did not look into it. Yeah, you're right. We did not look into it.
Well, if there are no more questions, let's thanks speaker again.
Thank you.
Yeah, thank you.
Так, you can switch off your share.
Let me see.
Thank you, Luan.
You're welcome.
Так.
Oh, yeah.
Окей.